Brandy Fiddler at TIDES, and I'm here with Carter Holt, Process Development Supervisor at Axel Labs. Today we're going to talk about Axel Labs' approach to endotoxin removal. Welcome.
Thank you.
My first question is, what is endotoxin and why is it important to remove?
So endotoxins are lipopolysaccharides that are frequently associated with gram-negative bacteria. They are known to be pyrogenic, meaning they induce fevers, and so it's critically important to remove these from any biological solutions.
Where in the manufacturing process can endotoxin be introduced?
Yeah, so anything past purification is susceptible to endotoxin removal, and so it's very important to move forward with these downstream processes as quickly as possible in order to mitigate the risk for potential endotoxin contamination.
So most of us know endotoxin is a lipopolysaccharide that is present or can be a contaminant in both peptide or oligonucleotide solutions. It is a known pyrogenic, so we want to, of course, either mitigate its presence or, in worst case scenarios, remove it. And so I have here displayed, it is contains a very wide range of sizes, anywhere from 10 to 1,000 kilodalton in size.
And what approach does Axel Labs use to remove endotoxins?
So our current approach is to use ultrafiltration diafiltration techniques, which is essentially using a membrane to filter out the endotoxin. So in this way, we retain our endotoxin on the UFDF skid, and we have the oligonucleotide product pass through that membrane, which we then collect.
Fortunately, there are a variety of methods for removing endotoxin known to date, one of which I have shown here is simply using charged filters. This is leveraged primarily for peptides, which are positively charged and could go through the filters. However, the filters will capture endotoxin, which is negatively charged under standard pH conditions. Obviously, this will not work for oligonucleotides, which are inherently negatively charged under those same pH conditions. Size exclusion chromatography can be utilized. In this case, we're leveraging the large size difference between relatively small oligos and relatively large endotoxin. However, this process can be difficult to scale, making it impractical for manufacturing size batches. Third one on the list here is ultrafiltration or diafiltration, where we're again leveraging the size difference between large endotoxin and relatively small oligos. And so this is where we're going to be focusing today. As pretty much I'm sure everybody knows, in a standard UFDF experiment, we're going to be using a cassette or membrane that is relatively small compared to the oligo of interest. And the oligo will be retained on the system while you're performing either a concentration step, diafiltration step, anything like that will be released to the permeate. The reverse logic would then be applied for an endotoxin removal experiment, where we're now going to be using a cassette that's much larger than your oligo of interest. And in this way, the endotoxin, in theory, could be retained, and the oligo would be removed in the permeate. So just to highlight here, in all experiments performed, we're using the EndoSafe Next-Gen MCS instrument to measure endotoxin in all of our samples. This work was broken up into 3 stages to demonstrate scalability without unnecessarily wasting material. So we began here with a small-scale study using the Amicon centrifugal filters, testing the permeability of oligos through these filters, both at a 30 and 50 kD membrane. We then moved on to a proof of concept using an active flux TFF skid, and then demonstrated this as at bulk scale as well, using the larger active flux 6 TFF skid.
Did you run this more than once?
Yes, in our lab we've run this several times, and we found that we were able to reproduce this on multiple scale ranges, anywhere from tens of grams up to hundreds of grams, with endotoxin removal of highly contaminated samples up to 99%, with about 90% product recovery.
So now that we demonstrated that we could do it at bulk, we did have a few more questions that we wanted to answer, so we went back and performed actually one more proof of concept experiment. And the goal of this experiment was to demonstrate, one, reproducibility, that we could do it more than once at this scale, but then also we wanted to demonstrate that we could reuse these cassettes because we have basically, every time we do that second pass, we'd have been installing a new fresh cassette, which can be costly and maybe unnecessary. So in this experiment, we used the same cassette for all passes. One other thing about this sample that was a little bit different was that we took the harvested material that was from the previous endotoxin experiments, the material that was left on the skid, and this was the material that was used. So we're actually starting with a much higher endotoxin, in this case at 42,000 EU. In this experiment, we actually ran 3 passes rather than just the 2 because we wanted to see how far we could push or how far we could reduce endotoxin. And indeed, we were able to reuse the cassette. You can see that after the first 2 passes, we're already at 99.95%, and by the 3rd pass, we nearly removed all of it here at 99.99%. Otherwise, we were able to show as well that our process is reproducible and successful.
Great. Well, thank you, Carter, for being here.
Thank you for having me.